Hello and welcome back to High Peak Education. I would like to perform a video where I give you some intuition about how torque relates to moment of inertia and how moment of inertia relates to angular momentum, and we'll investigate each of these rotational dynamics quantities. So let's go ahead and start with torque. I've discussed torque in a previous video, but I'd like to look at torque as it relates to force and radius directly, and I'd also like to apply this to this following turntable. So what we have here is we have a ladybug at a radius of 2 meters and a beetle at a radius of 4 meters. I can apply a force to this turntable and I can accelerate it. You'll see that the velocities will always be tangent to these bugs, but notice that the linear velocity of the beetle will be twice as much as the ladybug because he's at twice a radius compared to what she is. And so we'll see this as we go throughout. Notice the acceleration initially will be a combination of the centripetal and the tangential accelerations. Furthermore, we can also say that when we apply this force, we'll get a torque, and it's going to depend upon the radius that the force is applied in order to determine how much torque is applied. So let's go ahead and see if we can examine this. I'll first try to apply this torque right here at about a radius of 2 meters, and let's go ahead and examine the results. Okay, so hopefully you saw that the acceleration was a combination of centripetal and tangential. Let's go ahead and take a look at the graphs for now. Notice that the force was constantly increasing from 0 to 2 newtons, and the torque was approximately increasing from, 0 to 4 Newton meters. Why is that? Because that's 2 newtons times 2 meters for the radius. Also note we're in uniform circular motion right now. The acceleration is centripetal, the velocity is tangential. The centripetal acceleration is larger at a larger radius since both these bugs have the same angular velocity. Okay? And notice that the tangential velocity is larger for the beetle than the ladybug like we predicted. Let's go ahead and now apply a negative torque. Now a negative torque, instead of torquing it counterclockwise to accelerate it, let's go ahead and torque it in the negative direction, that is clockwise. So we'll apply this brake. So let's go ahead and do go again, but now let's apply this brake. Notice that the torque is a force at a certain radius, but the radius was much larger in this case at the outer edge, namely 4 meters. Notice that we also saw the acceleration, that there was a tangential acceleration in the opposite direction of the velocities. Okay, so let's clear these graphs and let's perform a slightly different experiment. Let's accelerate these bugs at a radius of 4 meters. So we should have twice the torque, thus twice the angular acceleration, so we should get to a much larger speed if we still take about that 1 to 1.5 seconds to go from 0 to 2 newtons of force. So let's try this. Okay, so hopefully you see this. Notice the turntable is turning a lot faster now because the torque was applied at a much larger radius. Notice the force it actually went a little bit higher than 2 newtons in this case, but it's not extremely different than the first experiment. But indeed, the torque is twice as much as it was in the first experiment. It's close to 10 now because the final force was about 2.5 newtons. Multiply that by 4 meters, that's 10 Newton meters for the maximum torque. Again, these bugs are in uniform circular motion with the tangential velocity of the beetle twice as much as that of the ladybug. The centripetal accelerations are also quite a bit larger now since the angular velocity is larger. Now let's apply an even larger force than the first experiment to give a negative torque. So let's do go and let's watch. So there we see that this negative torque and this thus negative force caused this thing to slow down quite rapidly. And you saw that there was a large tangential component opposite the direction of the velocity. Okay? So torque does not just depend upon force, it also depends upon radius, and we can have positive or negative torques. Let's now examine this if we instead have changes in the moment of inertia or the rotational inertia. So now what I have here is I have a turntable with the same bugs at the same radial locations, but now we're going to look at the torque and the moment of inertia and the angular acceleration. So we can change the outer radius or inner radius. We can change the platform mass. We can also apply a force on the brake. We'll show those vectors again, and the units here are going to be in radians, not in degrees, because that's SI units. So let's in fact spin this turntable up, kind of similar to what we did before. So let's spin this turntable up, pretty similar to what we did before, and we'll examine the torque and we'll look at the moment of inertia. Okay, so that's kind of similar to what we did before. Now notice the moment of inertia is staying constant. It's 0.809 kilogram meters squared. So notice that there was angular acceleration of the platform at first. Let's examine that. So notice that at first, when there was a torque, we were accelerating the platform in an angular sense. There was angular acceleration. Okay, so notice that when the angular acceleration went to 0, that's because the force and the torque also went to 0. But now let's change the moment of inertia of the platform. Let's make it so that there's less mass in the center, that it has a greater rotational inertia with the same mass, but at a larger radius. So we'll decrease the inner radius, and we'll go up to about the level of the ladybug, so about 2 meters or so. And let's now see what happens if we proceed. Notice things are a little different. Notice that not dramatically, but slightly different. Notice that we didn't apply any torque, and we zoom in here on the angular acceleration. There's not much that we see. But look what happened to the rotational inertia. The rotational inertia went up suddenly. When we have the same mass, so let's assume somehow miraculously we have the exact same mass, but we have an inner and an outer radius, much more of the mass is at a larger radius than it was before. So the rotational inertia is greater. Okay? So let's in fact clear and reset everything here for a second. And let's go ahead and have a look here when we have, and let's make the inner radius quite large. So this is almost like a hoop. So in fact, let's make it a hoop, shall we? If it's now a hoop, where the inner radius and the outer radius are almost the same. So in practice, real hoops do have an inner and outer radius, but the difference between the inner and outer radius is so much smaller than the radius of the thing itself. We usually just say the hoop has all its mass at one radius. Okay? So notice that what we'll do is we'll spin this up, and we'll see that this has a large rotational inertia. And in fact, it's going to be quite hard to spin up because it has a large rotational inertia, and thus the angular acceleration will be very low, even though we'll apply the torque. By the way, let's put the platform mass back to 1 kilogram, or sorry, 0.1 kilograms. So let's go ahead and start this to be spun up. So 3, 2, 1, let's go. Notice, did you see that it was quite difficult to spin this up? The angular acceleration was actually quite small most of the time. And even though we were applying a torque at a large radius, that's a pretty large torque, this is quite a large rotational inertia. Look at it. It's 1.549 kilogram meters squared. Now let's go ahead and stop, and let's go ahead and see if we add back that inner radius. So if we add back that inner radius with the same mass, we suddenly have less rotational inertia, quite a bit less. So let's see what happens in this experiment. Notice the rotational inertia is quite a bit less, but look at these bugs. See how suddenly they have a much, look at these bugs. See how they have a much larger centripetal acceleration and tangential velocity? Okay, that really should be due to the fact that they're going to be moving faster. So this turntable is moving faster, because that's like taking the same mass and bringing it in closer to the center. The angular velocity is greater because these bugs don't change their radius. But if mass is brought towards the center, that is, the moment of inertia is decreased and the angular velocity should increase. Okay? Now it's not reflected in the torque, but let's go ahead and see, perhaps. So right around here. So let's zoom in. Was there a torque? So there should have been a torque. So there should have been a rotational force. Okay? And then was there an angular acceleration? Well, there should have been, because the angular velocity increases, okay, for these bugs, but it's not shown on these graphics. So I'm not exactly sure why that is, but this is indeed what we observe, okay? What we observe is that with more mass now at the center, that change in rotational inertia, you should have changes in the angular velocity. Okay, and in fact, let's examine that in a greater detail. So what I have here is I have a depiction of an ice skater rotating on an axis. Notice that the reason we use an ice skater is because we want to ignore the effects of friction. We only want to focus on the effects of changing the rotational inertia. Now remember, rotational inertia is typically the symbol capital I, and we could change it from the initial rotational inertia to a maximum rotational inertia or a minimum rotational inertia. Now notice, a minimum rotational inertia is very similar to the experiment we just did before, where we decreased the radius of the mass, and thus the angular velocity should increase. Now why is that? Well, this is what we call the conservation of angular momentum. All the torques are internal. There is a torque because we definitely do move faster in terms of, there definitely is a torque because we do move faster in terms of our angular velocity. But the thing to keep in mind is that in the same way linear momentum, there were forces, they were all Newton's third law forces, that is internal forces. All the torques are internal. So the ice skater is not going to drag her skate against the ice. That would be an external friction or an external torque. She is only going to perform internal torques, but those internal torques are going to actually come from her moving her arms. Thus, her muscles are going to change her rotational kinetic energy. So when she decreases her rotational inertia, her angular velocity should go up, and thus she has the same angular momentum, but notice she's got a much larger angular velocity because her rotational inertia is less. So she performed work bringing her arms inward so that her rotational kinetic energy got a lot greater. But again, her angular momentum is constant. And that's just by changing the radius of the mass and thus changing the rotational inertia. Now what about if she puts her arms outward? Well, it's just the reverse of what we're talking about. She puts her arms outward, she's got a much larger radius, thus her rotational inertia is larger, and her angular velocity should be less, again, and then now she performs a negative internal torque by extending her arms, but notice that, again, her arms had to do negative work. She just basically allowed her arms to fly outward, if you will. Okay, so that's the idea with conservation of angular momentum. Let's look at this in a slightly more mathematical way. So what I have here is a way to depict angular momentum. Notice that this is very similar to the mathematics of torque, except that this is not a force, this is the linear momentum. And here is the angle, and this angle will be in relationship to the position vector from the origin, and phi is the smallest angle between that position vector and the linear momentum. Notice if we increase the linear momentum, indeed the angular momentum does increase, but notice it's quite small right now because the radius vector and the linear momentum vector are roughly parallel. So we might add linear momentum to this particle, but not angular momentum. What if I change the angle? What if I make the angle closer to 90 degrees? Well, it's more perpendicular, and there we go. We're at as close to 90 degrees as we can be, possibly. So at 125 degrees here, because I think this radius vector was about, say, 33 and a half or so degrees, notice that this is going to be as perpendicular as possible, so that gives us the largest angular momentum possible. Again, an angle smaller than 90 degrees is not as much of an angular momentum. An angle larger than 90 degrees doesn't give as much an angular momentum change. But again, as close as we can to 90 degrees will definitely give us a large change in the angular momentum. The direction is given by r vector cross p vector. R vector is the position vector, p vector is the linear velocity vector. Also notice that the direction axis is perpendicular to both of them and given by the right-hand rule. Since r vector and p vector in the xy plane, the L vector is in the z direction. It's either going to be the positive z or the negative z direction, depending upon what the right-hand rule tells us. If you increase the linear momentum now, indeed you can see the angular momentum also gets larger. So what that means is, if you have a particle, you can determine its angular momentum by doing r cross p. Or you can determine it by mv, that's linear momentum, times r times sine of the angle between them. If we want negative angular momentum, we should have the angular momentum vector with its axis pointing downward. That's because the linear momentum should give a negative cross product. That should be clockwise rotation as opposed to counterclockwise rotation. And what if I made the angle over here somewhere? I could get it to be perpendicular over here somewhere. And the idea is that it's going to be perpendicular, but it's going to be, again, I swung all the way around to 304 degrees. So 304 degrees from the x-axis. But again, the smallest angle between them is about 90 degrees. Now it's negative, so we end up getting with a negative angular momentum. That's because it's clockwise rotation. And then if I increase the linear momentum, you see a large negative angular momentum. So let's see if we can confirm that final experiment with the turntables and the bugs as before. Notice that we should have the conservation of angular momentum in this case in the absence of any external torques. If we suddenly make the mass go closer to the center, the angular velocity should go up. That's this omega, and the moment of inertia should go down. So let's see what happens. Let's go ahead and get this torqued. So we should have a certain angular velocity. Okay, so the angular velocity to me looks like it's about 4.153 radians per second. The moment of inertia is 1.549 kilogram meter squared, and the angular momentum is about the multiplication of those, about 6.435 kilogram meter squared. Let's stop. Let's decrease that inner radius. So notice that the angular velocity is going to go up. So there we see it. And then the rotational inertia should go down, but the angular momentum should stay constant. So let's go ahead and go. So look at that. the angular velocity is greater, the moment of inertia is less, the angular momentum stayed put. And just as confirmation, look at that. Suddenly the angular velocity went up. So there were internal torques that caused these bugs to move faster because more mass was brought toward the center. So hopefully this makes sense in terms of rotational dynamics, torque, moment of inertia, angular momentum, and so on. Thank you very much for watching this video. Please smash that like button if you enjoyed this content. Please subscribe to the channel to grow the channel. Thank you for watching High Peak Education. I look forward to your comments, and I will see you in the next video.